So in question 3, we focus on decision trees. So create binary decision trees. Technically are just decision trees where the terminal nodes are 0, 1, or true or false, since we're doing Boolean functions, for all the Boolean functions in question 2, part 2. So basically all of these functions, in which the truth tables you've already created. We're going to do this using the ADDlib tool. But before we do that, let's look at what a decision tree is. So there are 5 key things to note about a decision tree. First thing is the number of nodes that are going to be in a tree. So if you have n inputs, so this n represents the number of inputs, you will have 2 to the power n minus 1 nodes. So let's say you have 3 inputs, x, y, and z. You will have 2 to the power 3, 8, minus 1 equals 7 nodes. And the number of layers to your tree is n. So again, the number of inputs. If you have 3 inputs, you'll have 3 layers. You will have terminal values, which will be 0, 1, or true or false. And you will have 2 to the power of n terminal values. So again, if you have 3 inputs, you will have 8 outputs, or terminal values. False, I generally go to the left. This is not set in stone. You can go to the right if you like. And it's represented by a broken line. And true, I generally go to the right, and it's represented by a solid line. Whether you go to the left with false and right with true, or right with false and left with true, is up to you, but you must keep it consistent. You can't go to left with false in one, and then the next time go right on false. So just keep it consistent. And the decision tree always starts with a single root node, which is actually why it's 2 to the power n minus 1, so you only have one node, or the root node. So let's just show an example. Let's start with the first question we had in part 2, which was just x. So output. So when it was 0 and 1. So when it was 0, we outputted 0. When it was 1, we outputted 1. So let's draw this as a decision tree. So a decision tree always has a name. So we'll call this one 1 bit, because we have 1 input. And we always start with a single root node. And we can just connect to that single root node like that. So this node is x, because it's our input. We have 2 to the power of n minus 1 nodes. 2 to the power of 1 minus 1 is 1. So that's all the nodes we have. We have n layers. So 1. We only have 1 layer. So we're actually done. Now for our terminal values, we have 2 to the power of n. So that is 2. 1 and 1. So we have 2 terminal values. We can see over here that they're 0 and 1. What we'll actually represent them as here is true and false, just to stay with the ADDlib. You can use 0 or 1, whichever suits you best. And from x, when x is false, you get false. So for false, I always go left, and it's a broken line. So, like that, and then true was over there. And that's it. That's our decision tree for 1 bit. Now let's show this in ADDlib. So when you start your system, you go to view, you go to scaled mode, so it fits your screen. Go to CS5024, go to Sync01, that's 0, and click the Sync icon. I am running this on 4 GB of RAM currently. You will see here that the Project Explorer is empty, because this is just a way Eclipse IDE works with workspaces. You have to actually import them back in. So you actually do is you go to import existing file projects into workspace, click next, click browse, and there's the current workspace, and you can just click OK. So all these are actually already created for you, so you just have to click OK and click finish. And it will bring all the project folders into your Project Explorer. And down here, you can click the bottom little squares down here. It'll show the building of these projects. And what you're going to actually get is a number of red X's over all these folders, because we're still missing one crucial project folder. But once it's finished building, I'll show you how to bring that in as well. Okay, so that has finished building. So now let's bring in the next folder that we need. So go to File, go to Import, Existing Projects into Folder. If you don't see that immediately, it's General, Existing Projects into Workspace. Click Next, go to Browse, and this time go back to CS5024. Go to CS4101 folder. Go to AdLib Material, Projects to Import, Synco project, and click on this Boolean Logic project and click OK. Then just click Finish. And now it will build the workspace once more, and you will see all the X's will disappear from all the other projects, and a red X will appear over this Boolean Logic project. So you can actually ignore that one. I will pause the video once more as it builds the workspace. You can see here at 1%, that'll get to 100. You'll see all the other ones, all the red X's disappear. One thing to note, going back to this, for the directed acyclic graphs, this is actually for binary decision diagrams. So for decision trees, you have branching. And you have, say, root nodes, and terminals. So this would be branching. This would be a false branch. This would be a true branch. You have nodes such as the root node, and you're like in different layers, you have different nodes, and then you have terminals. So for directed acyclic graphs, we're talking binary decision diagrams, and for decision trees, we're talking branching nodes and terminals. So going back to our image, as you can see, this has now been built. You still have the red X over the Boolean logic. Right click, go to Run As, Eclipse Application. You'll see again an empty folder. Go to File, Import, Next, Browse. Go back to CS5024, then go to CS4101, AdLib Material, Projects to Import, Eclipse Projects. And for this lab, we're doing ADD Lib Lab 1 Basics. Click OK, and let's click Finish. That is it. Now, we are concerned with the Decision Service Model folder. Inside this, you will see our predicates, which have been created for you. So you have X, Y, and Z, same as our question. We have our diagrams, which where we will create our decision trees. As you can see, the 1-bit and 1-bit not have been created already. And we have our classifiers, which have been created already, so you don't actually have to worry about these. So going back here, we can see our 1-bit decision tree has already been created. So when x is true, we get true. When x is false, we get false. And the 1-bit not is also created. So when y is true, we get false. And when y is false, we get true. So this is the not operator. So let's see how we run these two. So back on the classifier page, go up to graph model and click generate code. And you'll get code generation successful. Now if you run this from this diagram page, you'll get an error. Actually no, run code successful. A lot of times you'll get an error. So traditionally go to this classifier page and go graph model generate code. After that, go to source, boolean example, application.java. And from here, go to run and just click run. You can also click Control F11 or also this green tick over here. And you will see this little GUI will pop up. And we want to check the 1-bit and the 1-bit not. There we go. And let's add in the AND. You notice that's 100%, but that's actually not true. So what you want to do, if you want to add in a new classifier, is you close it, run again, and then select your 3 and click start. Because you have to refresh the memory. So now we're getting 74%, which is what it should be. So let's click stop here. What this is saying is your 1-bit is correct against the reference classifier, which was a classifier that was made earlier. 1-bit not, also correct, 100%, but our AND is wrong. We're only getting 75% accuracy, so there is an issue with our AND implementation. Now if you look at the console, you can see, let's go to one where they differ on the end. Like here. So our 1-bit, when x is true, our output should be true, and your classifier is true, and the reference classifier is true. And not is false, so when y is false, the output should be true, your classifier is true, reference classifier is true. So they're both correct. Now when x is true and y is false, the output should be false, because it must be true with AND. But your classifier is saying it's true, and the reference classifier is saying it's false. So there's an issue with your classifier. This is where the issue is. So to solve this, go back to the diagrams, scroll down, and you will see the 2-bit AND. So this is clearly not correct. So we can delete that and delete that. So what do we need? Coming back here, we can now delete this. And we don't need this just yet. So let's do AND. X, Y, output. And this is X and Y. So 0, 0, 0, 1, 1, 0, 1, 1. Output is 0, 0, 0, 1. Also, just a quick note, if you're wondering why we do 0, 0, 0, 1, 1, 0, and not 0, 0, 1, 0, 0, 1, it's because in binary this actually is 0, that is 1, that is 2, that is 3. This is all we're actually doing on the input side. We're just counting up to 3 in binary. And if you, starting at 0, if you have 3 inputs, we count up to 8 in binary. So it'd be 0 to 7, and so forth. That's why You start with the zeros first and then go on to the ones. So now, how many inputs, or how many nodes will we have? This time we have 2 inputs. So 2 to the power 2 is 4, minus 3, minus 1 is 3 nodes. We're going to have n layers, we're going to have 2 layers, n is input. And 2 to the power n terminals, so we're going to have 4 terminals. So, we always start with the root node. There's only ever one root node. But we need 3 nodes in total, and we've only 2 layers. One layer is gone. So in our second layer, we need our next 2 terminals. Which makes sense if you think about it with x. So you can have false or true. So what you do when x is 0, and then you got the y values. What you do when x is 1, and you got the y values. And now, we have our layers. We have 2 layers. So this in here is the layer section. This is just the name of your tree. This is the root node, x. And below this, we have the terminals. So, for this y, we can have a true, we can have a false. From the other way, we can have a true, and we can have a false. So, dot, 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 dot. So, when x is 0 or false and y is 0, we get 0. So, false. When x is 0 and y is 1 or true, we get false. When x is 1 and y is 0, so 1, 0, we get false. When 1 is true and y is true, so 2 solid lines, we get true. And that is our decision tree. So let's go make this in the ADD lib. So we want to open up, let's close this, our predicates folder. So click the drop down and see your X, Y, and Z. So you see we need 2 Y nodes. And then connect. Else is for false, see the dotted line. Then is for true, solid line. And we can see here, we only have 2 terminals currently, so we need 2 more. Else, then. Else, then. And then just click save. It does actually work. You actually can generate the code from this diagram. Go to application, click run, 2-bit and, click start. And you see if you generate from the diagram folder, it doesn't update your Boolean service. So click stop, close. This is why you must do it from the classifier page. Because if you do it from this page, generate code, now you've actually updated the actual code model. Now if we go to application, click run, and click end. Now we're getting 100% accuracy. So that's why you don't run it from the diagrams folder, you run it from the classifier page. Click stop, and now we've got 100%. Stop. Now, let's add in, let's do the 3-bit question. So X and not Y and Z. Let's write out our table first. X, Y, Z. 0, 0, 0, 0, 1, 1, 1, 1. 0, 1, 1, 0, 1, 1. Zero, one, 0, 0. So this is X. Output is X and not Y and Z. This is why this is 1. So X is true, not Y is true. But this was 0. I'm looking for not Y. So 0 is true in this case. And Z is true. If you want to think about it another way, you can think of this as 1, 1, 0, 0, 1, 1, 0, 0. So this would be not Y. So you can see 1, 1, 1 is true. And it's an AND, so they all have to be true. But traditionally, you write just it as X, Y, Z, but in these values, again, you're counting from 0 up to 7. So this is 0, 1, 2, 3, 4, 5, 6, 7. And when it says not Y is true, it's whenever it's a 0. A 0 is a 1, and a 1 is a 0. That's what the not does. So, how many inputs do we have? We have 3 inputs. So, that means we have 2 to the power of n minus 1, 7 nodes. We have 3 layers. We have 8 terminals. So we have our 1, 2 layers so far. So we need a third layer. We've already used 3 nodes, so we must have 4 in the third layer. Which again makes sense. When X is false, Y is false. When Y is false. Sorry, when Y is false, Y is true. When Y is false, and Y is true. So every node in a decision tree has to have a true and a false branch. So it's just a branching protocol. So every layer you add on, you're going to get for the previous nodes twice as many. So if there's 1 in the first node, you're going to have 2 in the next layer. If you have 2 in this layer, you're going to have 4 in the next layer. And you'll have 8, then you have 16, 32, etc., etc. So Z, 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 Z. We have 8 terminals, again, true, false for all the Z's. So we have 1, 2. So 0, 0, 0, 0 is false. In fact, all of these, whenever X is 0, it's going to be false. 1, 0, 0, false. 1, 0, 1, so 1, 0, 1 is true. Then false, and then false. And that's all it is for tree. So let's go over and build lab diagram. Sure, let's run it as it is. Let's see what we get before we change it. 40, less than 40% accuracy. So as you can see, we only have one node in there so far, so we need to delete them. So we need 2 Y nodes. And we need 4 Z nodes. And we need a couple of terminals. We need 8 terminals, as I said earlier. Turn that over there. You can actually just copy and paste. You click Control C, click over here, Control V, and it'll actually copy them instead of dragging them down all the time. So this will always be the same. 0 goes to the left, else 0 to the left, else 0 to the left, else. This one, right, through, right, through, right, through. 0 to the left, right, true, 1 to the right. It's here. False, true. Else, then, else, then. So you can all see I go 0 to the left, 1 to the right. That's what I always do. So here you have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Which is exactly the same as our table here. This is what we're doing. You're basically just representing the table as a decision tree. Click Save. Go to our classifier. Graph. Generate code. Successful. Application. Run. 3-bit function. Start. And there we go. We have 100% agreement with the reference. Click Stop. And that is it for this lesson. I want you to complete all the other examples. They'll be similar to the AND example from earlier with 4 bits with the majority of them. And all you simply have to do is build the decision trees for all of them. I like to write them out first and then build them in the ADD lib. But once you build them, generate the code and then check against the reference classifier to see if they are correct. You should get 100% accuracy if they are correct. See you for the next part.